In the previous capsule, we learned the definition of a conservative vector field. Those are the ones who are gradients of scalar functions. However, we do not know yet how to determine whether a given vector field is conservative. In this case, for problem 19 of homework 6, we will determine if the vector field in question is conservative. For 2D vector fields, the criterion is as follows. A 2D vector field with coordinate functions pq will be conservative if the x derivative of q matches the y derivative of p. For our example, we will check whether the vector field f is conservative. We have that py is the y derivative of 3x squared, but 3x squared with respect to y is a constant, so this is 0, while the x derivative of q is the x derivative of y cubed, and this is 0. As these two quantities match, we have that the vector field is conservative. Now we would like to determine which is the potential function of f. To do that, we will integrate both components with respect to x and y to see what could be a candidate for a potential function. Remember that if a potential function exists, then we have that if f was the potential of large f, it happens that the gradient of little f is f, and this only happens when f sub x, f sub y equals 3x squared y cubed. So we must integrate this component with respect to x to recover f, and this component with respect to y to recover f. Observe that the integral of 3x squared with respect to x is x cubed. And remember from Calc 1 that we should add a constant. In this case, as f is a multivariable function, it could be that that constant is a constant depending entirely on y. So let me call this plus c of y. Then we should differentiate this entire expression, but be concerned especially about the constant function in terms of y, and see how it could match up with the other term. This is our candidate for the potential. Differentiating this with respect to y, leads us to this function c prime of y, but this should also match this expression y cubed. It must happen then that the integral of c prime of y is the integral of y cubed, and now we just get a true constant of integration. We then have that the original function, the potential, is f of xy, which is this old amount, x cubed plus c of y, but we have that c of y is the resulting function after integrating c prime, and we have that this is what we get, y to the fourth over 4 plus a constant. The end result is x cubed plus y over 4 to the fourth power plus a constant. Observe that if you differentiate this to take its gradient, we return to the function that we had originally, 3x squared y cubed.